In continuation to our earlier discussion regarding application of digital human modeling software in different types of industries or occupational sectors. So already we have discussed about application in automotive industries. Now we are going to discuss application of digital human modeling and simulation in the field of healthcare industry. Presently, this digital human modeling software are being used in various aspects of healthcare simulation, and this is used for healthcare education, medical training, medical research and practices. And in many of these cases, not only digital human modeling software, but also various virtual reality systems are being used. In these both the digital human modeling and virtual reality are used together in many cases for all these purposes. Now, in subsequent slides, we are going to discuss about how digital human modeling software is being used by various researchers in healthcare industry for either for medical training or medical education or for different types of medical practices or medical workplace design. So now we are discussing a particular paper written by Marcus et al. 2006. So in their paper entitled Computer Simulation for Ergonomic Improvements of Laparoscopic Surgery. In this paper, Marcus et al. Demonstrated how digital human modeling can effectively be used towards ergonomic design of laparoscopic operation room to ensure increasing overall safety and efficiency by reducing the postural stress of the medical staffs. So here we will discuss by various images taken from this paper how they have used this digital human modeling technology. Since continuous observation of screen and positioning screen position on the bulky trolley with equipment is mandatory for each member of the team, they have to undergo awkward posture and static working posture for prolonged duration. In laparoscopic surgery room, the surgeon as well as nurses or clinical staffs, they have to undergo awkward working posture, and that is also static in nature for prolonged duration, because there is requirement they have to continuously look at the screen for performing their activity. So in the research reported by Marcus et al., they used CATIA software for modeling operating room and Ramsys software for developing digital human model. Apart from these two softwares, specimen software is also used for extracting 3D wireframe model of the working posture from two synchronized video spots of different viewpoints. These models are used for providing posture to the mannequin in Ramsys software. So while those medical staff or surgeon working in that workplace, then videography was taken, and from that videography, two video frame from two different viewing angle are taken, and on those video frame, this type of wireframe model was put by specimen software, and in that specimen software, that 3D wireframe model ultimately developed. That 3D wireframe model developed from specimen software was actually used for developing digital human model in Ramsys software. So specimen software, what actually in this case specimen software did, specimen software developed the wireframe model from the 2D images, and that wireframe model ultimately used for developing 3D digital human model in Ramsys software. Then an ideal working posture of the surgeon was defined based on the demonstration of comfortable posture by two experienced surgeons. three different positions of the screen are simulated with Ramsys software. So there are three images. In the first images, this is the actually screen or display where both in this workstation in laparoscopic surgery room mainly three people are involved. One is surgeon and two are the medical staff or nurses. So here this yellow color one is the display or screen, then this green color one is the Maya board, and so in their study they simulated three scenarios. In one case the display is kept diagonally where the surgeon can see, but this is not comfortable to visualize by medical staffs or nurses. In another case, it was kept just opposite the surgeon, backside of the medical staff. And in the third case, it was positioned towards the head side of the patient. In this position, surgeon as well as medical staff can see this display, but they have to turn their neck. So these three simulation conditions are considered, and then various types of ergonomic evaluation are performed by the researchers. Following the simulation, various aspects of operation room design are evaluated in terms of position of the image displays, monitor for the nurse and the assistant, distance between image display and observer, height of the image display, operation room table and Mayo stand. Next, operating table height, height of the Mayo stand. So all these factors actually considered during this simulation study. So here various component A, B, C, D in this image A, B, C, D, E has been mentioned for various components of this workstation or workplace. So the team, as I mentioned, the team consisted of three members. One is surgeon, that is B, this one, then assistant C, and this is assistant C, and next the scrub nurse, that is D. So these three persons are involved there. In this particular design, the surgeon is situated at the right side of the operating table, and the assistant and the nurse are situated opposite to him. So one side surgeon is there, and opposite side scrub, that nurse and that assistant is there. The patient is in prone position on the operating table. The image display is, this is the image display, and this green color one is the Mayo stand. So this is the overall setup in that operation room. So present research discovered that operative team for standard laparoscopic observation, laparoscopic intervention should have at least two separate image display. So following this ergonomic evaluation in that simulated environment, so researchers found that at least two image display are required. This is A and A1. Otherwise, it is very difficult to give comfortable view for both, that is the surgeon and also for nurses and assistant. So two image display are very essential. Digital human model. So following their study, they concluded that digital human modeling study not only limited to one field. Its perfect example is this present case. Although in this particular case study, Ramsys software has been used, which is mainly popular for automotive industry, because Ramsys is good for automotive ergonomic evaluation, but the same Ramsys software has been used in this case for laparoscopic surgery operation room design. So this is an example which indicates that the Ramsys software or any software developed for a particular industry is not only restricted to that particular industry, it can be used for other industry also. So in this image, it is showing the optimal solution for the position of the image display for nurse and assistant, that is A1. This display is for nurse and assistant, and this display A is for surgeon. This is an additional image display to the image display for surgeon A. So total 2 displays has been used in this case. So overall, so what we can find? So in their study, Marcus et al. Through that simulation study, they clearly demonstrated that what should be the optimal position of the display. At the same time, how should be the height of the myostand, operation table, and various other factors as described here, so that people who are involved there, that is the medical staff, nurse and the surgeon, they can do their work comfortably. In another study by Hanson et al., they demonstrated how digital human modeling tool can be modified and used to evaluate bathing system design for caretakers and caregivers from ergonomics viewpoint. So their research paper entitled Application of Human Modeling in Healthcare Industry. In this paper, they described how digital human modeling software can be used for designing a bathing system from the viewpoint of ergonomics. Anthropometry, joint range of motion, description and appearance of the mannequin are customized to represent caretakers and caregivers in digital human modeling tool, that is Delmia V5 human. So in their research, they used Delmia V5 human model, and various aspects, that is anthropometry, joint range of motion, all these things are customized to represent caretakers and caregivers. Digital human model personas are created for both the groups, that is the caretakers and caregivers. The standard appearance of the mannequin as it is appeared in digital modeling software, that was kept for caregivers, but a more aged corresponding appearance was given to caretaker, was given for the caretaker mannequin. So this is the caretaker, who is taking the care, and this is the caregiver, that is the nurse. So in this case, whatever appearance of the digital human modeling software is available in Delmia software, that has been the same thing has been used for caregivers, but for the caretakers, more aged appearance was provided. Preferred bathing posture was identified from the real life observation and used for this simulation. Tasks performed by caretakers and caregivers are also defined. After the study, the project was aimed at designing a new footrest to be integrated in the new bathtub design. So following their analysis, they ultimately proposed a new bathtub design, where they also proposed for integration of a footrest, that is shown here. So this is the first, Hanson et al. Studied the bathing posture. Based on the bathing posture, they provided the bathing posture to the digital human model, and this is the bathtub, and then they went for different types of ergonomic evaluation like ruler analysis, and based on the ruler analysis, it was possible to identify that which body parts are beyond the comfort range of movement, while caregivers are adopting various types of postures for their activities. So after these two papers, now in another paper entitled Ergonomic Assessment of Patient Barrowlifting Techniques using Digital Human Model. So in this paper, Kao et al. 2013 conducted a comprehensive assessment of barrowlifting technique using digital human model. So first we should know what is this barrowlifting technique. This is actually patient handling technique. There are different types of patient handling technique. One of those patient handling technique is barrowlifting. In barrowlifting, two helper or nurses are required. One of them actually hold below the neck and one hand at the waist region of the patient. So first these two nurses or the staff, they first put their hands together, one hand of this person and another hand of this person. They put this hand together below the waist region of the patient, and another hand is kept below the neck position and another arm of the second person is kept below the thighs. So in this way, in barrel-lifting technique, they hold the patient. In this research, they demonstrated that how these barrel-lifting techniques is affecting the posture and at the same time their spinal load while they are handling the patient. So JACC software was used for simulation of lifting activities. Throughout the study, a trunk flexion angle of 45 degree was maintained. And what analysis has been done here? Mainly low back analysis. This is the one ergonomic evaluation tool in JACC software that is used for compression force analysis at the lumbar 4 and lumbar, in between lumbar 4 and lumbar 5 segments. So these two analysis has been done. One is low back analysis and another is the comfort analysis. So these two analyses are carried out for evaluating their activities. Independent variables for the study are percentile of the patient weight and height. So three percentiles of the patients are considered: 5th, 50th and 95th, and accordingly their weight and height are considered. Next, percentile of the clinical staff. They are so 5th percentile, 50th percentile, 90th. Here also 3 percentile clinical staffs according to their weight and height are considered. Clinical staff's position are categorized into one towards the head side, another towards the foot side. Mean one towards this person towards the head side of the patient and another person towards the foot side of the patient. Then clinical staff's gender, that is male and female. So ultimately total 36 treatment combination came. So this 3 percentile into this 3 percentile condition multiplied by 2 staff position multiplied by 2 genders. So in this way 3 multiplied by 3 multiplied 2 and multiplied 2. So total 36 treatment combination are studied in this particular research. These 35 treatment conditions, patient handling conditions are shown in this particular table. So 1, 2, 3, in this way total 36 combinations are there, and for each of the combination ergonomic evaluation for lower back analysis and comfort analysis are performed. This is the screenshot from that JACC software where L4, L5 intervertebral disc compression force was calculated, and this image shows for different body joint angles whether those are in comfort range or not. If that particular joint angle is within the comfort range, then it is denoted with green color, and if it is beyond the comfort range, then it is denoted with yellow color. Cow et al. 2013 assessed how these independent variables, affect on the clinical staff's low back, compression force and postural comfort during barrow lifting technique. So already we discussed this one. Next, so this is the actually observation from that low back spinal compression force, and this is the treatment condition. So as we discussed, treatment condition or patient handling condition, the total 36 combinations are there, and for each of the combination how is the low back compression force that was measured. So recommended limit for low back compression as per Nash lifting equation, that is approximately 5000 Newton. In many cases, it was observed that it is beyond the recommended limit or beyond the acceptable limit in these three cases. On the other hand, there are also some cases where it was below the recommended level also. The result of this research showed that clinical staff in larger weight and height percentile, that is mainly male, experienced higher low back compression force. So male person with higher percentile values of height and weight, they suffered more from low back compression force. For a 95th percentile patient weight height, the head position clinical staff member experienced higher low back compression force than one in the foot position. So while they are handling 95th percentile patient height weight, then it was found that among these two clinical staff, the person who is positioned towards the head side, his low back spinal compression is more than the one who is in the foot position. While the trunk of clinical staff member was exposed to higher flexion angle that were still in the comfort range, the comfort ratings associated with the trunk, thigh and elbow are outside the comfort range. The result of this research could be applied in designing lifting protocol training programs with the aim of reduction in the risk of developing low back injuries. So in this research, through this digital human modeling simulation, authors was able to demonstrate that how the patient handling can be evaluated in terms of low back spinal compression and comfort, and accordingly decision can be taken that what types of modification is required to avoid these low back injuries. Next, we are going to another research paper reported by Kouchi and Muchimaru 2011. Their paper entitled Simulation of Body Shapes After Weight Change for Healthcare Services. In this paper, Kouchi and Muchimaru developed a system to simulate the body shape after weight gain or loss with the intention to motivate people to follow healthy lifestyle and adopting health actions. Research reported by them mainly targeted middle-aged males because this study was performed in Japan, and in Japan these middle-aged people are mainly middle-aged male persons are mainly exposed to overweight condition, and the persons who are considered for this study, their age range is starting from 30 years to 59 years. They are categorized in three groups: age below 40, age within 40 to 50, and age more than 50 years. The body shape after weight change was simulated by following method. So a body shape model was created for each subject by fitting high resolution template meshes to his scanned anthropometric data obtained from 3D body scanner. A digital human model called DHAIVA, that is Digital Human Aided Basic Assessment System, was used as the template. So for this, body shape representation, first what they did, they scanned with the 3D body scanner, they scanned the body of that particular person. Then on that particular person's body, on the scanned image, they positioned or fitted the high resolution template mesh with the help of this digital human modeling software called DHAIVA. From scanned image, ultimately they got this type of high resolution mesh image. The model are used for principal component analysis by multiple regression equation to estimate principal component score from 9 selected variables. Those 9 selected variables are weight, height and 7 circumferences of the body. So after this, after the body shape model, so they created this body shape model and also performed the principal component analysis to calculate the principal component score from 9 selected variables. Then 7 circumferential dimensions are calculated after weight change. So while there is weight change, either addition or reduction, while weight change happen, then again 7 circumferential dimensions are calculated using linear regression equation. After that, principal component scores after weight change are calculated from 9 selected variables, as we mentioned earlier, that is the height, 7 circumferences of the body and changed weight. Based on these 9 variables, principal component score are calculated after weight change, and body shape was reconstructed based on those principal component scores. So as I mentioned earlier, so first scanned image 3D body, with the 3D body scanner, first they collected the scanned image of the body, then on that scanned image of the body they fitted the high resolution template mesh with the help of this software, and after that this is the following the principal component analysis, they change the body shape of the digital human model. This is that. So C is the adjusting the posture and segment length of the body shape model. So this is the initial body shape after weight change, either weight addition or weight reduction. This is the body shape model based on the principal component scores. This model was further adjusted based on the body length of the body segments, and also it was adjusted for various body circumferences. So adjustment of the reconstructed shape model was performed by modifying 7 circumferences as per the estimated values and keeping the length of the internal skeleton of the body shape model unaltered. So while this body shape, meaning this is the reconstructed body shape after the weight change. In the reconstructed body shape, as the height of the body will not be changed, only there is addition or a reduction of the soft tissues. So skeleton dimension was kept fixed. Body circumferences, which are estimated based on the linear regression equation, this body total 7 circumferential dimensions are adjusted to achieve this final model. So this final model actually represents how a person will look after the weight change. So this was the initial look, and after the modification, how was the modification after the weight change, how he or she will look. In this case also, in this particular image, it is shown comparison of scanned body shape. This is before and this is after. So for a person whose height is 169 centimeter, weight 69.5 kg, and basal metabolic index is 24.3, and simulated body shape after weight increase. How much weight was increased? 15.5 kg. When for this person, when 15.5 kg body weight increased, then this is the body shape. So their system can demonstrate this type of body shape after the weight change. So if we define that this much weight has been increased for a particular person, then how he or she will look. Similarly, the system can also be used for weight reduction also. The simulated body shape after weight change demonstrated by Kouchi and Mochimaru 2011 was based on principal components derived from inter-individual variation. So their system was actually dependent on the inter-individual variation of body shapes. Principal components derived from inter-individual variation of the body shapes. Thus, sometimes the reconstructed body shape was found unnaturally different from original body shape because it is dependent on the inter-individual variation. But in real life, what is actually required, that is intra-individual body shape variation. Mean for a particular person, when for he or for her there is a weight change, then how will be the body shape after that weight change? For that purpose, we need the principal component analysis for intra-individual variation. So thus, sometimes the reconstructed body shape was unnaturally different as it was followed or it was based on inter-individual variation. So Kouchi and Mochimaru mentioned that longitudinally collected body shape database is required, that is the intra-individual shape variation, to solve these issues, so that unnatural body shape would not come if we can use the intra-individual shape variation. The study is expected to be usable in fitness club for motivating people to start and continue physical exercise or adopting healthy lifestyle to combat with overweight or underweight condition. Because their system, ultimately a system which they developed, that system is capable of representing that how someone will look or how someone's body shape will be changed due to weight change, that can be easily demonstrated by their system. So if someone come to this in front of this system, and if they find that after this much addition or this much reduction of the body weight, their body shape will look like this, that then they will be inspired that okay, they inspired to do regular physical exercise or changing their lifestyle. Cho et al. 2012 in their research paper entitled Analysis and Evaluation of a Combined Human Exoskeletal Model under two different constraint conditions. In this reported research, they generated a combined human exoskeletal model and performed dynamic analysis for two motions. One is lifting and another is carrying. Under two different constraint, that is two different constraints, one is strap condition, another is no strap condition, using musculoskeletal simulation of Anybody software. To predict the effect of strap, connecting them in how that strap affecting a person while he or she is using that exoskeletal system. To take into account the motion data of actual workers in the dynamic analysis, the act of moving and lifting a 14 kg object was analyzed using motion capture system. So in this image it is shown that two work activities are captured through motion capture system. One is transport or carrying motion and another is lifting motion, lifting the object from the table. In both this was recorded with 3D motion analysis system. Next, human body model was generated by Anybody software and exoskeletal robot was designed using SolidWorks CAD system. So two softwares they used. One is Anybody software for digital human modeling and SolidWorks CAD software for designing the exoskeletal. The exoskeleton robot model was imported into Anybody software. Information regarding weight, center of gravity, momentum of each segment as required by the required for dynamic analysis are determined from SolidWorks software and entered in Anybody software. To exert force on each joint, the exoskeletal robot model used a motor for each joint by creating a virtual muscle that can generate torque. Mechanical constraints are also applied to attach the human model with the exoskeletal system. Combined model was generated with two different types of dynamic constraints, and that results of the analysis are compared. So dynamic analysis, for dynamic analysis, two constraints are considered. One is no strap case, another is strap case, and in both the cases dynamic analysis are performed and compared to each other. So first one is the no strap condition. The human body or human model and the exoskeletal robot are bound only at hands, the feet, and at the waist in these 3 points. So exoskeletal in no strap condition is defined as the condition where exoskeletal model is attached with the human model at these 3 points: hands, feet, and waist. And strap condition are defined as the human body and the exoskeletal robot are bound at the upper arms, forearms, thighs, shanks, in addition to the no strap condition. So in no strap condition, all the 3 places where it was already there was a strap. Apart from that, additionally the straps are attached at upper arm, forearm, thighs, and shanks. So here from this image we can see conditional contact elements in case of strap case. The conditional contact elements in the Anybody software are used to generate the contact forces that are exerted between the human body and the exoskeletal robot in accordance with the dynamic constraints. Dynamic analysis of transporting and lifting motions are conducted using objects that weigh 0 kg, 10 kg, 20 kg and 40 kg respectively with the help of Anybody software. So in the next step, dynamic analysis was performed for both the activities, that is transportation and lifting, for various load condition or weight condition. So here you can see this is the transport and this is the lifting, while the combined model mean both exoskeletal human model attached with the exoskeletal model is carrying an object, and here is the lifting of the object. The ground reaction force was calculated for combined human and exoskeletal model. Most of the forces are exerted on the hands and the feet when there are no straps. In no straps condition, so 2 straps we mentioned in the earlier slide, that one is no strap case, another is strap case. During no strap case, most of the forces are exerted only in the 3 points, that is the wrist joint and ankle joint, because there are total 3, their connections are at 3 points, that is the wrist and joint, as we mentioned in no strap condition. So it was attached at the hands, feet and the waist. As only at the 3 point exoskeleton is connected with the human model, so most of the forces are exerted on hands and the feet in no strap condition. The wrist joint and the ankle joint bear a significant load in this case. When there was a strap, means strap condition, this load is better distributed in various body parts, because in this strap condition various body segments are actually attached through the strap with the human model. In general, it was found that the joint torques for wrist joint and ankle joint are reduced in both the motions in case of strap condition. During both types of motion, while straps are connected, heavier the object, lead to greater stress on the human body. Although the degree of stress was acceptable for all load conditions during lifting, but risk of injury was considerably higher in case of transportation. From this study, it was concluded that performing a simulation-based analysis on the reaction force exerted by exoskeletal robot on user would reduce the product development time and cost and help ensure the safety of the product. Following their observations, Cho et al. 2012 recommended the use of strap for exoskeletal while there is requirement of handling an object of large mass, as strap are found to be lessen the fatigue. So ultimately from their research they found that if straps are used to attach the exoskeletal model with the human body, then it can lessen the joint fatigue in comparison to the no strap condition. So, and based on that observation, they recommended that it is better to use the strap condition while the workers are handling larger loads or larger masses. Now we are going to another research paper where also digital human modeling software has been used for healthcare purpose. In this case, the title of the paper is A Virtual Human for Lower Limb Prosthesis Setup. In this research, Colombo et al. 2011 demonstrated the use of virtual humans to validate lower limb prosthesis design and functioning. They first described the state of the art on virtual humans techniques and main features of the new design framework which they proposed for prosthesis design, then the application of virtual human for prosthesis setup. Key elements of their proposed design framework are digital model of the anatomical district, that is the residual limb for socket modeling, and the amputee's avatar to validate the prosthesis design. These are the two key components. The framework guides 3D modeling task of the prosthetic design around the patient stump and the selection of standard and custom fit prosthesis components depending upon the patient's characteristics, that is anthropometric data, prosthesis to be used, daily use or sport activities, and stump morphology. So in that they have developed framework. So first they developed a framework to guide the people who develop the prosthesis. So in their system, modeling the framework guides a 3D modeling task of the prosthesis socket design around the patient stump. So if you look at this image, so what is required for prosthesis design, the overall framework is given here. So database of patient characteristics mean his anthropometric data, his prosthetic condition, then dimension of the stump, all these informations are provided. So that is actually used as knowledge based framework, and various types of rules are also considered for prosthesis design. So that is the first step, and then those data are used for various purposes. So the people who are designing the prosthesis, they collect 3D CAD models of various prosthetic components that from the database of the standard parts, mean prosthesis parts. From the standard database that is already developed and stored as the CAD models, From those database, the required CAD models for various components of the prosthetic limbs are collected. This area is coming under prosthesis modeling lab. So, in prosthesis modeling lab, first step is to identify the parts of the prosthetics from standard parts database. And next, another is virtual socket lab. In virtual socket lab, first information regarding the stump body part is required. So, for that MRI scan data of the stump portion is first taken. From that wireframe mesh is generated, and on that stump model, so first in virtual socket lab the stump model is generated. On that stump model, the socket is designed in the CAD software. So, first through the MRI scan, stump model is generated. From the stump model, then the socket is designed. After socket, while that socket is designed on the stump body parts and the standard prosthesis components are ready, then this is sent, all these components are actually sent to virtual testing lab. In virtual testing lab, virtual testing of the assembled parts with the human stamped body parts or this prosthetic assembly is attached with the digital human model for virtual testing different types of gait analysis or motion analysis. Main steps for the new design process: first, acquisition of patient characteristics, that is health condition, stump condition and anthropometric measures of the amputee. This information is used by the knowledge based framework. So, this is that middle portion. In the middle portion, all these informations are collected. Then socket design creates 3D virtual model of the socket around the stump digital model acquired with the reverse engineering equipment. This step foresee socket modeling assistant and finite element analysis tool to study the stump socket interaction and verify its functionality. So, this in virtual socket lab, the ultimately this socket is designed following this socket design process. Selection of standard components. The framework drives the user to the selection of standard components from the for the considered patient. So, this is that CAD lab. In that CAD lab, that standard components are selected for that particular patient. Then prosthesis assembly. The system finally assembles the socket 3D model and the selected standard components. So, 3D socket model, this is the socket model and the standard components are assembled. Next, to create and simulate the patient's virtual human life mode software are used. Virtual testing, an avatar of the patient wearing the prosthesis is created, by which it is possible to execute prosthesis setup and evaluate its functionality, simulating postures and movements. For virtual testing of the prosthesis setup, there are two steps. First, patient avatar characterization from the anthropometric and ergonomic point of view, and second is the gait analysis. Now, if we look at this image, so there are two parts. One is prosthesis modeling lab and another is virtual testing lab. In prosthesis modeling lab, So how, here it is mentioned that there are two steps of prosthesis. For virtual testing of the prosthesis setup, there are two steps. Patient's avatar characterization from anthropometric and geometric point of view. So how the patient's avatar is characterized. For this purpose, if we look at here, so first acquisition of anthropometric measures. That anthropometric dimensions actually help in first level of characterization of the avatar. Mean that is a digital human model. In virtual lab through digital human modeling software, we are creating the first level of characterization of virtual avatar. Then acquires stumps MRI. From stumps MRI, that MRI data, second level of characterization takes place for the avatar or virtual digital human model. So first, digital human model is created as per anthropometric data. Second, it is modified as per the information for the stump body part. Then third level of characterization of the avatar with prosthesis. This prosthesis come from prosthesis modeling lab. So select standard parts and assemble prosthesis, that is the 3D CAD system. From 3D CAD system, that standard prosthetic assembled prosthetic parts come and it is attached with the digital human model. Then static alignment and gate analysis are performed. If everything goes correct, if the prosthesis, if it is found following the gate analysis and analysis in terms of alignment, if it is found that everything is right, then it is go for manufacturing or production. Mean prosthesis is validated, then it can be used. If it is from this analysis, if it is found no that prosthesis is not designed properly, then again there is modification of the socket model and modification in the select or changing the selection of the standard parts from the parts database. So in this way, prosthesis modeling lab and virtual lab actually helps in developing the prosthesis prosthetic limb for the amputee. So this is the digital human model. So if there is upper leg amputee, then this is the first digital human model is created through this. In this case, as we mentioned, we used this LiveMod software. With that software, anybody software. With that anybody software, yes. So with this anybody digital human modeling software, this is the initial human model. Then when there is amputee case, then this is for upper leg amputee and this is for lower leg amputee. This model is created. Then with that model, that based on the MRI scan, stump body parts, that is the residual portion of the bone, is identified and it is attached with that model. Similarly, this is for lower leg amputee. In that case also, stump body part is attached. Then there is attachment of the soft tissue in case of upper leg amputee as well as for the lower leg amputee. After that, that prosthetic or prosthesis is attached with the socket. Similarly, in this case also, prosthesis is attached with the digital human model. Then the final model becomes ready for both the upper leg amputee as well as lower leg amputee. When this final human model with the prosthesis is ready for both the cases, that is transfemoral model as well as for transtibial model. When both are ready, then these are used for movement analysis and alignment analysis, that is gait analysis as well as alignment analysis, whether this prosthesis is aligned properly with the in relation to other leg. To create and simulate the patient virtual human life mode software was used. So in this, this digital human model which has been used in this particular case, that is the life mode software. Virtual testing. An avatar of the patient wearing the prosthesis is created by which it is possible to execute prosthesis setup and evaluate its functionality, simulating posture and movements. Two test cases have been considered. A transtibial amputee, that is 35 years old, 170 centimeter tall, and a transfemoral amputee, 49 years old and 175 centimeter tall. So this is the, as we mentioned, this is the example of the transfemoral model, how it is developed, and similarly this is the tibial model, how step by step it was developed. In order to verify the potential of virtual amputees, simulated movement of the patient, that is walking and sitting on a chair, were created using the law of motion library available in life mode software. To achieve accurate simulation of the muscle and joint movement, an inverse dynamic simulation was recorded for the target body segments, that is the links. These compiled movement histories were then used for the forward dynamic simulation of the prosthesis limb. So first, for the for inverse dynamic simulation was recorded for the limb, for the right limb, and from that limb the compiled movement histories of the dynamic motion are compiled and used for forward dynamic simulation of the prosthetic limb. It can be concluded that the product development process which has been described here could improve the prosthesis design, simplifying and speeding up the technician task. So earlier what used to do, technician has to go for trial and error method, and in that case there was bothering of the patient because that this type of socket has been designed by trial and error method by the technician, then it is attached with the human body, then different types of trials are performed with the real human subject. But as the whole prosthesis design as described in this image, the whole prosthesis design method is being performed in the virtual environment, so it is very much helpful for the technician to find out the right or correct prosthesis design, and also it is possible to analyze how whether the designed prosthesis limb will be effective for the normal movement of the patient. It was so here from this image you can see transfemoral walking simulation which this author performed, and also transtibial sitting on a chair. So both the task, one is walking, another is sitting task, was simulated in life mode software, and those prosthetic assembly was tested, and then it was understood that these prosthetic organ or prosthetic parts can be used by the patient. It was noticed that digital human model permits to reduce number of prototypes. In fact, a computer-aided approach allows virtually carrying out several tests of the traditional socket development process that are very bothering for the amputees. So, from this research paper, it is very evident that digital human modeling software can effectively be used for the overall development process of the prosthetic limb or prosthetic assembled parts. And here are the references, various references which have been used for this various slides of the presentation. So in this particular section where we are discussing about the use of digital human modeling for healthcare application, only few research papers we have discussed here, but there are thousands of research papers reported by various researchers. So I suggest all the students who are undertaking this course, please go through all these as many as papers you can read to understand that how these digital human softwares are nowadays being used for healthcare education, healthcare practice, healthcare workstation design, and then only you will be able to use digital human software effectively for your own design purposes. After discussing this healthcare industry, now in the next section, in the consecutive slides, we will discuss about how digital human learning softwares are being used by various researchers for general industrial applications. Industrial design of industrial workstation have been revised based on study characteristics, analysis and evaluation tools, modeling approaches and results achieved. So this was reported by Longo and Montiel in 2011. Simulator 2009 described evaluation of industrial plant layout considering 8 workstation, 14 workers who are involved in making high pressure hydraulic hoses. So these are the few images from different research papers where digital human learning software has been used either for factory layout or manual material handling, product evaluation, user interface evaluation. For in various cases, the digital human learning software has been used. Manual material handling and user interface evaluation are evaluated using method time measurement, OWAS, overwork working analysis system, lift analysis in EM workspace software. It was reported by Santos et al. 2007. Biomechanical analysis was also done with their own developed model, that is SIMM, having scalable human model, motion capture, inverse and forward kinematics. So this was reported by Okimoto in 2011. So from this slide, we can get overall idea that various researchers are using digital human learning software for industrial workstation or for different types of activities performed in those industries. So in their research, in a book chapter written by Ambrose 2009, the title of that book chapter is Advanced Measurement Method in Mining. In that book chapter, Ambrose described how digital human modeling can be effectively be used towards ergonomic design and evaluation of various machines and equipment used in mining sector. Coal miners are at risk from being struck by mining machinery due to confined workspace. Researchers use digital human model to increase miners' safety while working around the machines. Rope bolter operators in underground coal mines have a high incidence rate of being struck by the rope bolter's drilling boom. Ambrose 2003 and Ambrose et al. 2005, in those reported literatures, it is found that they used motion analysis data and digital human model to analyze accident risk of miners working with rope bolters, manipulating key factors that influenced injuries, including the speed of the rope bolter boom, boom direction, vertical space constraints, and work postures, operator location, operator size, and hand positioning behaviors when operating the rope bolters. So here from this image, it is shown that digital human model while they are using that rope bolter, then how is their posture and what type of activities they perform. Eager et al. Used unobscuration zone and coverage plane features of digital human modeling software which is an effective tool for evaluating line of sight of the earth movers, yielding better understanding of the underground machine design. Ambrose et al. 2004 effectively used digital human model to evaluate severity of muscle recruitment and spinal load while operating a rope bolter in different work postures and mine seam heights. They generated a database containing L4, L5 spinal joint and back muscles by processing captured motion from test subjects using digital human model. Their study results showed that operators' forward bending movements increased significantly from a standing posture, while the compression force and trunk muscle activity are greater from the in comparison to kneeling posture. So from this image you can see, while the kneeling posture workers are working in kneeling posture, that is relatively better instead of the standing posture, because in standing posture the bending is more. As the bending is more, there is more compression at the intervertebral discompression at L4, L5 segment. Bartels et al. 2007 applied digital human model vision tool and survey data to define the value attention location. Their observation provided preliminary recommendation for control observations that enhance VAL, mean value attention location, enhancing safety and reducing health risk of mining equipment operators. In their research paper, Case et al. 2009, that research paper entitled Hadrian Fitting, that is the name of the software, Hadrian Fitting Trials by Digital Human Modeling. In this paper, Case et al. Described about the Hadrian, a digital human modeling system which uses discrete data set for individual rather than the statistical population. So in this digital human modeling software, instead of statistical population, they used discrete data set of the individual anthropometric dimensions. They also demonstrated the application of system with a focus on elderly and disabled and their potential exclusion from public transportation system. Hadrian system provides two important ergonomics aspects, that is, use of individual set rather than the population statistics such as percentiles of anthropometric and other data, and means of describing the interaction with the product. So in this Hadrian software, two important aspects are considered, that is, one, instead of using percentile anthropometric data, they used the individual data set of the targeted population, and at the same time they described the interaction between human and the product through task description process. The data collected from the earlier study pertaining to anthropometry, joint constraints, reach and mobility of aged and disabled people are used in the present research to represent the target population. This is a screenshot from that system, Hadrian system, examples of various windows for specific individual in the Hadrian database. So for movement of the body joints, then clips of the task performed by the actual person, reach envelope. So various aspects are shown in this particular screen. And the data collected from a population of aged and disabled people, So this is that representation where various types of members are there with their various types of capabilities and physical dimension, and this database was actually used for their demonstration purpose, that how individual body dimensions or individual work capabilities is actually affecting in performing various types of tasks. Hadrian contains the database of individual and task description method to execute the evaluative capabilities of underlying semi-human modeling system, as though a real fitting trial was being conducted. The task and its evaluation criteria are defined using a simple task description language, and the subsequent analysis uses these task description to create and drive a human model to evaluate their capability in performing that task. So this is the task description screen. So various types of task for a particular activity can be defined using this task analysis window of the Hadrian software. On completion of the task analysis, the percentage of the individual of the integrated database, from the integrated database, the percentage of the individuals who can perform that particular activity is actually estimated. If there are person or people who are unable to perform that particular activity as is defined by the task description, as is defined by this task description language, if it is found that the database which was considered, some people of the database cannot perform that activity, then those people will be identified. At the same time, not only identification of those people who are unable to perform those activities, at the same time the system will also identify and the situation which causing difficulty will be displayed with the suggestion for improvement. So who are the people who cannot perform that activity and why they cannot perform that activity, that will be displayed. In the current research paper, capabilities of the Hadrian system has been demonstrated with the case example of ATM machine operation and accessibility aspect of the public transportation system. These two case examples are taken into consideration. Potential barriers faced by the people during performing various activities of travel can easily be identified by this Hadrian system. From the database who make these journeys are being identified. So potential barriers faced by the people are identified, and accordingly we can modify the system or the facilities so that most of the people who are facing the problem can overcome those problems. Hadrian task description capabilities allow the modeling system to be used as an automated evaluation tool. Moreover, it allows for the consideration of issues beyond the physical aspects of anthropometry. So in this particular research paper, where Case et al. 2009, through this Hadrian system, they demonstrated that it is not always possible or not feasible to use percentile anthropometric data, because there are many situations where we cannot evaluate the product with percentile, because there are many situations while there is no good correlation between different anthropometric dimension, then we cannot use percentile anthropometric data for digital human model development. So, and this is very much applicable for aged and disabled population. So, for them, if we want to design or if we want to evaluate any facility or any workplace, then we need to use this type of Hadrian software where a specific database is used. In that database, instead of use percentile anthropometric data, individual set of anthropometric data of the persons are used, and their various tasks are then task is defined through task description language, and for each of the individual the task is performed, and from that analysis ultimately we can identify how many of those people can perform that particular task and how many of them cannot, and who cannot perform that activity, then we can find out that what's the reason behind that.